I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 16. Find the sum of all the digits in the number 2 to the power of 1,000. Before we start to write any code, let's approximate how many digits are actually in this number. We can determine how many digits are in a particular number with logarithm. The log base a of c is the quantity which, when a is raised to that power, produces the value of c. You can think of logarithms as being a sort of inverse to the exponent operation. If you're familiar with the root operation from which we get the square root, you may be wondering what the difference is. After all, both the root and logarithm are inverses of exponentiation. The difference is in which argument is getting inverted. When we take a root, we find the value which, when raised to the bth power, produces our result c. When we take a logarithm, we find the value which, when a is raised to that power, produces c. Addition and multiplication only have one inverse each, namely subtraction and division respectively. This is because they're commutative, so it doesn't really matter which argument you attempt to invert, you'll get the same inverse operation. But exponentiation is not commutative, so we get two inverse operations, one for each argument. Now, the number of digits needed to represent a given value x in base 10 can be given by floor of log base 10 of x plus 1. Let's take a moment to do a sanity check on this. The first two-digit number is 10, so if we plug 10 into this equation, we should get 2. Log base 10 of 10 is 1, which is already an integer, so the floor does nothing, and 1 plus 1 is 2. If we plug in a slightly smaller number, like 9, log base 10 of 9 is a number very slightly smaller than 1. The floor of that is 0, and 0 plus 1 is 1. Likewise, the first three-digit number is 100. Log base 10 of 100 is 2. Again, the floor function does nothing, so 2 plus 1 is 3. And for any two-digit number, log base 10 of that number will be some quantity strictly between 1 and 2, whose floor is 1, so the result will be 2. Now in our case, we want the number of digits of 2 to the power 1,000. So first we want the common or base 10 logarithm of this exponent. An exponent inside a logarithm can be brought down to the outside. Log base 10 of 2 is the power we must raise 10 to in order to get 2. This is a small number, certainly less than 1, so the resulting digit count is less than 1001. With a calculator, we can figure out that the number should have exactly 302 digits. A 300-digit number won't fit in a 32-bit integer. In fact, it won't even fit into a 64-bit integer. The largest signed 64-bit integer is 2 to the 63 minus 1, which is roughly a 20-digit number. If we're going to compute this directly, we're going to need big nums. Fortunately, lots of programming languages nowadays ship with big num support built in. Today, we'll write our draft in Julia. Julia is a high-level dynamic programming language, which puts it in a class with Python and Ruby. Though Julia is much newer than either of those, with its first official release only 11 years ago, in 2012, Julia was designed with data science in mind, and it draws heavy inspiration from existing data science libraries like Python's NumPy. If you've seen my video on J or Jelly, you've heard the term broadcasting. Broadcasting is the act of taking an operation that's intended for scalars, like numbers, and applying it pointwise to vectors, matrices, or other higher-ranked tensors. As an example, the plus sign operator is conventionally applied to numbers, but we can also apply it to a vector of numbers, or to matrices, and the resulting data structure will have the same shape as the inputs. Simple operations like addition and subtraction are broadcasted by default in Julia, which means we don't even have to do anything to get this behavior. For others, we can opt in to broadcasting with the dot operator. The multiplication operator in Julia is the star. When applied to scalars, it multiplies the numerical values, but when applied to matrices, it will attempt to perform matrix multiplication. If we want to apply scalar multiplication pointwise over the matrix instead, we use a dot to indicate our intention. It's not just built-in operators that can be broadcast over multidimensional arrays. Any function can be suffixed with a dot to enable this behavior, such as the sine, cosine, binary max and min, and anything else you can imagine. As a brief aside, I've thrown the word tensor out there, so let's talk about what that word means. Tensor is a scary word for a lot of people because it summons images of the hardest parts of your undergraduate linear algebra class. Without going into the incredibly complex mathematical background, when I say the word tensor today, all I mean is an array in some number of dimensions. The rank of a tensor determines how many indices are required to get scalars out of it. Put another way, the rank of a tensor is the number of dimensions it has. So a rank 2 tensor has 2 dimensions to it. A rank 1 tensor is just an ordinary list. It's the sort of thing you'd encounter in a non-array-based language like Ruby. Julia calls a rank 1 tensor a vector. A rank 2 tensor is the mathematical object we call a matrix. It's a two-dimensional array, and to index into it, you need 2 indices, the row and the column. Put another way, to indicate the size of a matrix, you would need to give me 2 numbers, its width and its height. So we say it's a rank 2 tensor. We can also construct higher rank tensors in Julia. There's no explicit bracket syntax for this, but we can construct them using several helper functions. To construct a rank 3 tensor whose dimensions are 2 by 2 by 2, we can write this. Undef indicates that the elements are uninitialized, so we'll effectively get whatever happened to be at that memory location last. This is useful if we're going to fill in the array with our own values immediately. Of course, the most common use cases are to generate an array of all zeros or all ones, and we can do that with specialized helper functions. If you want an array of some constant, you can simply multiply the ones array by it. So when I say tensor, all I really mean is multi-dimensional array. The actual mathematical definition of a tensor is beautiful and minimal, and I encourage you to go look it up and convince yourself that it means the same thing I'm saying, but for the purposes of this video, all I mean is multi-dimensional array. Do note that this is significantly different than a nested array. An array which happens to contain another array is not a multi-dimensional array, though it might look and act like one in certain situations. A true multi-dimensional array has a rank, which determines how many dimensions it has, and at each coordinate in the resulting shape, there is a scalar value. With all of that in mind, we'll be exploring how Julia actually implements all this broadcasting logic in a future video, but for now, let's focus on the task at hand. We want to sum the digits of the number 2 to the power 1000. Julia integer literals are 64 bits in size by default, but the language supplies a type called bigint, and we can turn an ordinary fixed-size integer into a bigint by calling the constructor function. We only need to do this once. Any mathematical operation will widen its opposite argument to a bigint if given one big number and one fixed-size value. So our input is bigint of 2 to the power of 1000. Then we want to sum the digits of this number. We start our digit sum variable at 0, and our loop is going to iterate until our input is 0. At each iteration, get the last digit by taking our value modulo 10 and add it to the digit sum. Then divide out the last digit. Note that regular floating point division is done with the / in Julia, like in many languages. Here, we want integer division, which is performed with the Unicode division sign. This program won't quite work yet, and the reason has to do with the subtlety in Julia's scoping rules. If we took this entire block of code and put it in a zero-argument function called run, then that function would work correctly. But Julia treats the top-level scope of your file differently. Like Python, Julia distinguishes between global and local variables. At the top level of a file, any variables you declare are global and will be treated as names available on the module you're defining. Inside a function, any variables you declare are locally scoped to that function and are not exported as names. This is also true of generators, comprehensions, let blocks, and do blocks, the last of which is basically the equivalent of a Ruby-style block. Conditional constructs like if, as well as the begin block, which runs multiple statements in one expression, do not change the scoping rules. However, looping constructs and try-catch blocks are a bit odd in Julia. They introduce what's called a soft scope. Soft scopes introduce a local scope if there's not already an enclosing local scope, but if there is, then they just use the surrounding scope without introducing a new one. So in our example with the run function, the function body itself introduces a local scope. Thus, any variables we assign to inside or outside of our while loop are treated as variables in that function. But in our original program, without the run function, we don't have a local scope, only a global one. So since we don't have a local scope, the while loop creates a new scope that shadows the variables outside of it. The simplest way to fix this problem is to prefix the assignments inside the loop with the global keyword, which indicates they should apply to the global variable and not introduce a new variable in the current scope. But this doesn't quite sit right. After all, the global scope really is for module-level functions and values. It's not intended as a sandbox for us to do intermediate computation within. Our nullary function isn't a bad solution, but we can actually get the same effect without a function. The let keyword in Julia introduces a new hard local scope, full stop. We can use it anywhere, even inside of a function, to get a new scope that's protected from the enclosing one. But we can also use it at the top level to introduce an explicit, hard scope. Then, when we hit our while loop, the loop is contained within a hard local scope, so its soft rules see no need to create a new variable scope. We get the behavior we intend. And this more closely matches our intention. If we turned this file into a Julia module for release, we don't want users of the module to be able to access the intermediate variables value and digit sum. We want them to be able to run our, albeit fairly simple, calculation, and that's it. With that tangent into Julia's scoping rules completed, this is a working program. And there's not really much in the way of optimizations we have to do here. We're going to target an esoteric programming language that has big num support today, so the size of the integer isn't a problem. Enter Labyrinth. Labyrinth is a two-dimensional programming language which puts it in the same class as Befunge and Hexagony. Further, Labyrinth's data model is stack-based, so our method of manipulating variables will be similar to that of GolfScript or CJam. Labyrinth has two stacks, the main stack and the auxiliary stack. Most operations act on the main stack. So when I say pops a value or pushes a value, you can assume I'm referring to the main stack unless I say otherwise. Both stacks start with an infinite number of zeros on the bottom, so if we were to try to pop from the main stack immediately, we would get a 0. A Labyrinth program models a two-dimensional maze. Every instruction is a single character, spaces and the boundary of our program are walls, and our lab rat starts in the northwest corner facing east. As the program proceeds, our lab rat runs the command at its current position and then advances in the maze. The advancement follows a few simple rules. First and foremost, if there's only one free neighbor of our current position, we should go that way. This is common at the start of our program or if we happen to hit a dead end. If there's two free neighbors, go the way we didn't come from. That is, simply continue in the direction we were already heading down the hallway. If 3 or 4 neighbors are free, we do a conditional branch. We look at, but do not pop, the top value of the main stack. If it's equal to 0, we continue straight ahead. If it's negative, we turn left, and if it's positive, we turn right. If there are only 3 neighbors and our chosen direction would run our rat into the wall, then the rat turns 180 degrees from the direction he wanted to go and continues that way. Note that all of these instructions are relative to the rat's current orientation, so when I say continue straight, that means continue in the current direction. It does not mean go north unconditionally. One useful corollary of this 3 neighbors rule is that if we hit a 3-way intersection from one of the 2 sides, we'll continue going straight if the top of the main stack is 0, or turn otherwise. This is useful since comparing against 0 is one of the most common ways we would want to branch. This navigation process continues until we hit the @ instruction, which indicates the end of our maze and the termination of our program. Now we know how to navigate our maze, and we also have a tool for doing conditional comparisons. Since this is a 2-dimensional programming language, loops are done by simply navigating back to the same point in the program. Let's talk about the commands available in our program. We won't need all of these today, but since it's a fairly simple language, we'll go over all of them briefly. The quotation mark is the simplest command, in that it doesn't do anything. It's just an empty square in our maze that the rat can navigate to. Remember that spaces are walls, so if we want the rat to be able to go somewhere, we need to put a quotation mark. The apostrophe behaves like the quotation mark, but it can be used for debugging with the right command line flags. We won't be using that today. We already mentioned the @ sign, which terminates the program when executed. Input and output is fairly straightforward in Labyrinth. The comma reads a single byte from standard input and pushes it onto the main stack. The question mark similarly reads a signed integer in base 10 and pushes it onto the main stack. On the output side, the dot pops a value, takes it mod 256, and writes it as an ASCII byte to standard output. We could use that to do a complicated printing loop like we did in BF or NASM, but fortunately we won't have to. The exclamation mark command pops a value and simply prints it as a signed integer in base 10. Finally, the / command prints a new line character to standard output. Labyrinth also provides the usual arithmetic operations of plus for addition, minus for subtraction, star for multiplication, / for integer division, and % for modulo. All of these pop 2 values off the main stack and push the result back onto the main stack. We also have the close paren, which increments the top of the main stack, and the open paren, which decrements the top of the main stack. Backtick multiplies the top of the main stack by -1. Ampersand, vertical bar, and $sign are the bitwise conjunction, disjunction, and exclusive OR, respectively. And the tilde command is bitwise negation. Like all of the other arithmetic commands, these operate on the main stack. The 10 numerical digits each perform the following operation. Multiply the top of the stack by 10, and then add the digit. We saw this same operation in hexagony, and it's designed to allow us to easily input multi-digit numbers. If our program consists of the sequence _1, 2, 3, 4 in order, then the underscore will push a 0 to the stack, and the 4 digits will operate on it. At the end of the operations, the number 1234 will be present at the top of the main stack. Everything we've discussed so far operates on the main stack. Now let's discuss how to manipulate our 2 stacks. Following the Baffunge convention, the colon duplicates the top of the main stack. Semicolon pops the top of the main stack and discards it. Open brace and close brace move values between the 2 stacks. Close brace pops the top of the main stack and pushes that value onto the auxiliary stack. Open brace is its inverse, which pops the top of the auxiliary stack and pushes the resulting value onto the main stack. With these 2 stack manipulation commands, we can use the auxiliary stack to get effectively random access to our main stack. If we want the 5th value down, for instance, we simply need to move the top 4 to the auxiliary stack, do something with the 5th, and then move the 4 values back to the main stack. The equal sign swaps the tops of the 2 stacks. And finally, the hash sign pushes the current length of the main stack onto the main stack, including only values explicitly pushed onto the stack. So the length of the main stack excludes the infinite string of zeros that start out on the stack, but it does include any zeros we chose to put on the stack. Finally, we get to the most complex part of Labyrinth. Anyone can navigate a maze, but any good Labyrinth has shifting walls. And there are 4 instructions in Labyrinth that shift the walls of our maze, and they all work basically the same way. Let's talk about rows first. The less than and greater than signs manipulate a row of our labyrinth. First, we pop a value from the main stack. This value tells us which row we're going to operate on. The row number is taken relative to the lab rat's current position. So row 0 will shift the rat's current row. A positive number will shift a row to the south of the rat, and a negative number will shift a row to the north. The actual shifting is done to the left for less than and to the right for greater than. If the lab rat is on the affected row, the rat moves with the row, and the element on the leftmost or rightmost position wraps to the other side of the maze. The caret and lowercase v do the same thing for columns, shifting up and down respectively. A negative index shifts a column which is currently to the west of the rat, and a positive index shifts a column which is currently to the east of the rat. These commands let us manipulate our source code during the runtime of our program. The code we're writing today for Project Euler isn't complicated enough to require them, so we'll be sticking with basic stack manipulation. With all of that in mind, let's discuss how we want our program to be structured. We need to do two things. Calculate 2 to the power of 1000 and then sum its digits. Exponentiation isn't built into Labyrinth, so the power function will need to be a loop. And of course, the digit summing algorithm is also a loop. We need 2 loops. This is the basic structure of our main program. The rat starts in the northwest corner. Our first loop will run until the exponent is 0 and then exit out of its southeast corner. Our second loop will run until our computed power is 0 and then exit out of its northeast corner. The program will end with an @ sign at the northeast corner. Let's get started. First, we push 2 and 999 onto the main stack. We start at the number 2, not 1, so our exponent starts at 999 to compensate for the fact we already have a factor of 2 multiplied into it. Now, we're about to hit our first intersection, and we want the rat to unconditionally head east or left from its relative perspective. So we need a non-zero value on the stack. Push 0 and then decrement so we have a non-zero value. Our actual intersection can be a simple empty square indicated by a quotation mark since we don't need to do any work at this moment. Now we're inside our loop. Discard the top value of the stack, which was just a placeholder to make sure we turned the correct way, then decrement our loop counter, which started at 999. Now we want to multiply our accumulator value, which is at the second from the top position on the stack. Move the top value, which is our loop counter, over to the auxiliary stack, then push 2, multiply, and move the loop counter back over. Now we hit another intersection. The loop counter is on top of the stack, so by the rules we discussed earlier, we're going to peek at the loop counter, but not pop it. We'll continue straight if the loop counter is 0, or turn if it's non-zero. In our case, if it's non-zero and we turn back around, we'll push the constant 1 onto the stack and head back to the beginning of our loop. The constant 1 ensures that we turn back into our loop at the northwest corner, rather than accidentally heading back to the very beginning of our program. Once we're outside our first loop, the stack contains 2 values. The top value is guaranteed to be 0 and was formerly our loop counter. Below it is the number 2 to the power 1000. Pop and discard the 0 since we don't need it anymore, then push a 0 onto the main stack and immediately move it to the auxiliary stack. This will be our accumulator for the sum of digits. Next, push a 0 onto the stack as a marker for our loop, so we continue straight when we hit the intersection. Inside our summing loop, pop the sentinel navigation value, then duplicate our power of 2, and take the top value modulo 10. This puts the last digit of the power at the top of the stack, while leaving the power itself unmodified below that. Remember that our digit sum is being kept on the auxiliary stack, so move it over to the main stack, add the current digit to it, and then put it back on the auxiliary stack for storage. Next, we want to remove the last digit from our value. So we push 10 and divide. Division in Labyrinth is always integer division, so we don't have to worry about decimals. Now we hit a T intersection from the side. The top of our main stack is the remaining digits of our number. If this is 0, we'll continue straight to the end of our program. If this is non-zero, we still have digits to process, so we head left, back into the loop. If we head left, we push a -1 onto the stack to ensure we turn left at the next T junction, and re-enter our loop. Once we're outside of our loop, the top of the main stack is 0. And the top of the auxiliary stack is the number we really want, our digit sum. Move the top of the auxiliary stack to the main stack, print it as an integer, and terminate the program. And that's it. This program gives us the right answer in no time at all, which solves Project Euler problem number 16 in Labyrinth. Be sure to tune in next time when we solve Project Euler problem number 17 in Flash-a-Lash, the substitution-based programming language.